Hello viewers, welcome to this video lecture on the course Complex Analysis. My name is S. Abinya. I am a faculty member in Department of Mathematics in Ratnam College of Arts and Science. Today I will give a brief introduction about complex analysis. So, in many universities, complex analysis will be introduced in the curriculum for the final year of UG program and the first year of PG program, because this course needs the basic knowledge on one variable real analysis and multivariable calculus. So, before entering into this course, you need some basic knowledge in these fields. Next, first, what is complex analysis? Complex analysis is nothing but it will analyze the field of complex numbers. Then what is complex number? A complex number is an algebraic completion of real numbers. So, you will be wondering, right, how it will be known as an algebraic completion of real numbers, right? I will explain it later. So, before explaining that, I would like to stress that what you have done in real analysis. In real analysis, you might have do all the algebraic operations, right? Then you can you can do limits, series, you can do, you have trigonometric functions, exponential functions. Likewise, you can do all these things in real analysis also. But there are some differences in complex analysis and real analysis. We'll study those things in great detail in the upcoming classes. So, let's see the origin of complex analysis. Let's see the origin of complex analysis. First of all, let's assume that you don't know negative integers, you only have positive integers. Then you have to find solve this equation x plus 2 is equal to 1. But you don't have a negative number. What will you do? X is equal to 1 minus 2, which is a negative number. So, at that time the negative numbers have evolved. So, let's assume that you have positive and negative integers, but you don't know anything about rational numbers. So, now you have to solve this equation, 2x minus 1 is equal to 2. The solution will be 2x is equal to 2 minus 1, which is equal to 2x is equal to 1, x is equal to 1 by 2. In that time, you need rational numbers, right? And that time, rational numbers have evolved. Next one. Suppose you have to you don't have irrational numbers, but you have to solve the equation x square minus 2 is equal to 0. So, if you want to solve this, you have x square is equal to 2, which means that x is equal to square root of 2. On that time, you need irrational number. Likewise, when the mathematicians are forced to solve this equation x square plus 1 is equal to 0, they needed to invent the complex number. So, if you want to solve this, you get x square is equal to minus 1. In real number system, you don't have any such a number whose square is a negative number, right? So, in that time, a complex number have evolved with the imaginary unit I with property I square is equal to minus 1. Next one. So, I have told you about complex number when we invented complex numbers, right? Okay, why should I care about complex numbers? Why should I study complex number? Why should I analyze that? You may think, right? So, yeah. using complex numbers you can solve differential equations. The real and imaginary parts of complex functions are very essential to solve the very important and famous equation del squared u is equal to 0, which is known as Laplace equation. No, I don't want to solve this equation. Means there are, if you want to solve a differential equation, there comes a Laplace and Fourier transforms. You will use Laplace and Fourier transforms to solve differential equations, right? This section you should have tools of complex numbers. So not only in differential equation, there are many important fields of mathematics such as fundamental theorem of algebra, the Riemann hypothesis are in need of complex numbers. Not only these applications, there are plenty of applications in the field of complex numbers. So what I want to stress here is complex analysis is such a powerful field. Next one. So we usually denote a complex number by alpha plus I beta. Here I is a imaginary unit. Alpha and beta are real numbers. I've already told you that I square is equal to -1. Here if alpha is equal to 0, you will call this number I beta as a purely imaginary. If beta is equal to, here beta is equal to 0, you have only alpha, where alpha is a real number. So it's a real number. So next one. So not only in the previous slide we have considered a complex number as an element of a field. So in complex analysis we can deal this number in plenty of ways. First one is element in a field. The next one is we can consider it as a point in a geometric plane, and also we can consider it as a two-dimensional vector space, and we can study its topological properties also. So in our curriculum we are going to see the properties in algebraic way and in a geometrical way and in topological way also. So we'll study many more algebraic properties of complex numbers in great detail in the upcoming classes. So the next one is the geometrical representation of a complex number. How can we represent a complex number in geometrical plane? So usually we'll denote a real number in a real line, right? But we will represent a complex number in two dimension, in a plane. The next one, in a plane with two axes. Here the x-axis is known as real axis. Here we will represent a real number. This y-axis is known as imaginary axis. Here will represent imaginary numbers. So together this plane is known as complex plane, or we can call it as Z plane. So we'll further study the geometrical properties. There are many fantastic properties. We'll discuss that in unit 2. There is a beautiful theorem which is known as stereographic projection. It's such a beautiful, wonderful theorem in complex analysis. We'll study all those things in great detail in the upcoming classes. The next, that's it for today. Thank you so much.